Hello. We are on our final topic for this topic set, and this is all about free fall. So if you remember our last videos, okay, was on constant acceleration. So we looked at how our graphs were doing this. Okay, so we saw a position time graph that went like this. We saw a velocity time graph that went like this, and then we saw our acceleration time graph do this. So this is my velocity, this is my acceleration. So again, we were looking at this and we said that this represents a changing a change in our velocity. The slope then represents this, and so these were all kind of interrelated. This was showing constant acceleration, this one's showing constant acceleration, and this one shows constant acceleration. So all three pictures show the same thing. Prior to that, we didn't have any acceleration, and so our graphs looked like this. So this was my position graph went like this, and then our velocity graph went like this. Okay, so this was showing no acceleration. So no acceleration in this one. Okay, this one shows constant velocity. And then if we didn't have any of that, we'd have our third situation where it was just a straight position time graph. Okay, so all of these types of graphs were our related way of talking about motion. Okay, it's the way we describe motion. So we have constant position, constant velocity, constant acceleration. Flat spots are always important. Slopes, constant velocity, constant acceleration. Slopes give us the step down. And then we only had this one that was our kind of curved ones. This is kind of how we're relating it all into our last topic. Now, free fall is really when we have constant acceleration. Okay? And it's constant acceleration because of Earth. Okay, so now again, we're back to we fall because there's gravity involved. So in other words, we're now getting into the whole concept of gravity. We kind of are going to start out where we talk a little bit about this whole constant acceleration. And you may remember that when we were doing our data collecting on this ramp, okay, so when we had our car on a ramp, the car went down there and we saw that kind of a curve that we expected to see, which shows that there's some form of acceleration there, and it's a constant acceleration. If we take that ramp and we change it, in fact here I'll grab my ramp right here. So if we change this ramp, okay, and we make the ramp get steeper and steeper, we see that it'll accelerate at a higher rate, okay? So again, the grade of our ramp gets to a point. Well, there's a limit to how far we can bend this ramp before we're essentially just doing this. We're dropping an object straight down. That's free fall, okay? And so that's when we get into this whole concept called free fall, okay? And it's just a form of constant acceleration. We have an accepted value for free fall on Earth. Now, this is, again, free fall on Earth, okay, is 9.8 meters per second squared. Okay, 9.8 meters per second squared is the accepted value for free fall on Earth. It looks like my laptop's dogging a little bit. Okay, so now I've got a picture of the Leaning Tower of Pisa here, and this is because this goes back to Galileo's experiment. So Galileo was the one who actually started to roll these balls down various ramps, changing this, and saw this relationship. Now he came about and he said, you know, if we in theory took these objects, and he was rolling big balls down there and sometimes they were small, and so we're talking about difference in masses, and he says it doesn't matter what the mass is. They all accelerate according to this constant acceleration concept. So mass is kind of an independent feature. So what he did is he said, and now there's no proven record of this, is that he went to the top of the Leaning Tower of Pisa. He took two objects that had different mass. Boy, my pen is really not working too well. So they have different mass. And he says, if I drop both of these objects and they fall straight down, they will hit at the exact same time because they have to cover the same distance with a constant acceleration. Same distance, constant acceleration. They're starting at rest. So in other words, they will achieve the same speed. Now this was the basics behind what we're calling gravity. And so he had basically did some experiments, came up and found from changing various angles the value of what gravity's acceleration was going to be, 9.8. And that's kind of how we went about it. So our big concept here is that all objects will fall at the same rate, independent of their mass. Now you might say, well, that isn't always true. I know that, if I, jump out of an airplane or something like that, I'll achieve this thing called terminal velocity, and that's something we'll talk about. Or that, a piece of paper won't fall at the same rate as a textbook would, okay? And so there's a couple of different things that we look at, and we have an issue with air resistance on our planet, okay? We like air, we like atmosphere, we need to have it in order to live and breathe, because we can't live on the moon. Okay, and now my next picture here is showing a picture of what we did up on the moon. And they actually did this as an experiment because they knew that the moon had no atmosphere, so there was going to be no air resistance. So they went ahead and they said, okay, well, let's take a hammer, okay, and let's take a feather. And these are obviously two items that have different masses, and if we take those two objects and we let go of them at the same height, they will accelerate at the same rate. And that acceleration rate will be whatever the gravity value is for the moon. And they did find out that it does work, and they both hit at the exact same time. The moon's gravity is less than that of Earth's. This is, of course, why you see them doing their balancing and things like that. But there's no air resistance. Now, when air resistance happens, though, that's where we get into some different things. And it actually stretches into topics at 4 when we get into talks about forces and we look at Newton and Newton's laws of motion. But on the moon, air resistance, none. Objects fall, hit at the exact same time, and we've got some documented proof, if you believe that we really landed on the moon. Okay, so now, as I was mentioning, we were talking a little bit about this whole thing called terminal velocity, and apparently there's a movie out there that has Charlie Sheen in it, with terminal velocity. I don't know if he was winning at that point in time or not, but it is Charlie Sheen. I can't say I've even seen it. But I can tell you this, I did jump out of an airplane, okay? And so I have experienced terminal velocity. Now, typically this is a graph of what we expect to see when we jump out of an airplane. We expect to start here with time equaling 0. We jump and then we accelerate, so we see this acceleration. Notice this is a velocity time graph. This is a velocity time graph. And so we see a nice straight line along this until we get to a point. So in other words, a straight line on a velocity time graph tells me that I have constant acceleration. And the slope of that acceleration is the rate at which I'm falling. That's my acceleration rate. Then it starts to taper, and we get to a point where all of a sudden we flatten out. So now you see that we get a flat spot. Flat spot on a velocity time graph says that I'm not changing my speed. I have constant speeds, constant velocity. That's terminal, okay? That's what we mean by terminal velocity. We're falling at the same rate. Now, when you jump out of an airplane, you essentially have air resistance that's acting on you. And it takes a while for that air resistance to kind of balance itself out. But you do hit a speed at where the up push from the air molecules is going to be equal to like your weight going down. So that's the only place where weight kind of goes into it. Again, topic set 4. But we get to that point where we balance out and we end up getting it. And it happens in about the first 5 seconds, 5 to 10 seconds that you achieve terminal velocity. I believe it's like 120 miles per hour. But then you fall for a while, okay? So we cover some distance. And again, we could figure out our displacement by area under the curve here. Then all of a sudden we pull our parachute. Okay, and the cool thing about this is I jumped with a camera guy, and so as the camera guy is going, you get this sensation. The sensation is that you feel like you're getting pulled up, but you're not. Okay, you're still falling. It's just that you start falling with less speed. You decelerate, so you have a deceleration. Camera guy and I are like eye to eye, and all of a sudden the guy pulls the chute, and all of a sudden, camera guy's falling like a rock still. And I just basically go like this. I'm still falling, but I'm falling at a much slower speed at some point. Then eventually, you steady out again. You achieve that terminal fall, okay, that terminal speed. And that's the time it takes for us to then get down. So again, that's terminal velocity. A lot of it we'll talk about again in topic set 4, but we are looking at constant acceleration. So it's a constant acceleration situation. All of our equations are going to work, and I'm going to actually kind of pause at this point. So this is my content video. Video B is going to be all with a couple of problems. I've got a couple of problems that I'm going to work out, and so you can watch that one. But you don't have to watch that one tonight. We can span that one out over the next night if you so choose. But I know I've got a couple of overachievers here that you're probably going to watch the video anyway. So until next time, and again, if you have questions, we'll address those in class, and have a good night.